associated. All right, last time we were talking about X-ray experiments and how do we actually get information from them. What's like the basic setup of an X-ray or a diffraction experiment?
Something
Yeah.
else, and you got film behind it.
Okay, so we have a source and we're shooting radiation at it.
Shooting radiation at our source.
Out of our source. I think I did. What region of the electromagnetic spectrum are we picking? Okay. We don't know why yet, but we will soon. Yep. The Braggs, one of the Braggs, he was working in his garden and he thought about this and then he went with X-rays because he wasn't seeing with other types of radiation. So that's at least the story associated with it. So if you're working really hard on problems, sometimes it's a good idea to take a break, take a breather, do something completely different. That's why when I go home, I refuse to read and I do completely mindless stuff like hitting rocks with a hammer or just dumb stuff. Or playing Cilantro, that's almost thoughtless. Cilantro is great, don't start it right now. Yeah, don't do it. Bad. Okay, what are we shooting X-rays at though? Yeah, so we have a crystal. We're drawing it like this, but it's not really, it doesn't have to be a single crystal. It could be a milled powder. Now, what happens to this? Yep, it diffracts. You get some that go this way, some that go that way, some that go that way. Even in fact, some will shoot back towards the detector. Why is it diffracting? Yeah, it's either passing through or it's hitting electron densities. And we measure this with some sort of detector, which we haven't talked about the detector yet. But in the past, we said, what did they use? Films. And I handed out a little handout that shows a diffraction pattern on it. Okay, but to really understand where those diffraction patterns are coming from, we have to, oops, I shouldn't have added an apostrophe. That's a no-no. Bragg's law. The Braggs won the Nobel Prize in physics associated for this. This is the equation. We're going to derive that equation today and figure out where it comes from. And then we're going to utilize it to explain what we're observing when we see these diffraction patterns. Now, a little bit of history associated with it. This was derived by the English physicists. Sir William Bragg. Yep. And his son. Also, Sir William Bragg. W.L. Bragg. In 1913. There's something magical about that time frame when science took a real big shift. That's where quantization started becoming a thing that people were observing in around that time frame. And it really changed the trajectory of science. Yeah, a little pre-World War I. And actually, it's amazing that some of the people who changed things, a lot of them served in World War I and made it through trenches. Thank goodness. Okay, so what is this used for? It's used to explain why X-rays or other forms of radiation are deflected in certain angles. So to do our derivation today, we don't need to understand wave functions, which means we don't have to understand complex conjugates. That will come later. For now, we can use trigonometry. It's worse. I also agree that it is worse too. I like my derivatives. I love my integrals. Trig is like something I have to knock the cobwebs off when I was totally not paying attention during high school. We're going to hit it, but we don't want to touch it yet because there's a lot of important things that come out of this. Okay, so we're going to assume we have a crystal that is just comprised of 2 atomic layers. Two layers. And then these atoms are spaced d apart. So a distance of d. So if we try to represent these, we're just going to draw our unit cell or our crystal. So there's our cool little lattice. The distance we're talking about is the distance between the planes, d. Okay, so they're that far apart. We have them listed here. Now, what we're going to do is what all good scientists do. Let's shoot some radiation at it. Okay. We will bombard the extal with 2 rays, X-rays, alpha and beta. Initially, these 2 rays are in phase with one another. And they have the same wavelength. Okay. What color do you want me to draw alpha and what color do you want me to draw beta? Yellow and blue. Okay. Here's alpha. Alpha zips down, hits that atom. What is going, we're going to mark the direction that alpha is going to because that's important. Okay, what is going to happen to that ray? Yeah, the pew, I like the sound effect associated with too. It's going to deflect. Beta. Beta comes in at the same angle, but it misses that atom in the first layer. It hits the atom in the second layer, and what happens to it? Yeah, pew! It will also bounce off.
So
Do they have the same what? They should. Okay, now let's talk about what happens. What's the difference between these two? Yeah, they're different colors. Yeah. What about their phases after this has happened? they're shifted. We won't say out of phase yet. They could be out of phase. They could be in phase, but they're shifted. Which one has traveled a further distance? Beta has traveled a further distance. Let's summarize that. So since beta has traveled further than alpha, and there's one more thing I'm going to add. We only care about maximum intensities. Okay? So, Katie, you said in phase or out of phase. I can't remember. Do you guys get constructive and destructive interference? Anybody need a review of constructive, destructive interference, or is it good? Solid? Okay. So now, we're going to hit these things, and what they were looking at were films. The brightest spots, or the only ones that we'll be able to see very well, like look back at your picture that we have. So if you look, which ones are the easiest to pick out in terms of that diffraction pattern? Here, Joe, share your picture with me. Yeah. So look at that. Where do you see, what can you see all possible reflections in there? Which ones are the darkest? Yeah, the one in the middle. That's actually a beam stop, so that way when you hit your detector, you don't burn a hole, because you will literally burn a hole into a film when you do it. So that one's the darkest. What's the next darkest one you see? Yeah, the second ring out. But can you see those other ones? Yeah, there are some other smaller ones that you can see, but they're hard to pick up. Now, that's a single crystal diffraction that you see there. Powders will have a ring, but there's only specific values. What ends up happening is you only want to look at the most bright intensities because there's constructive, destructive interference. Since you're throwing so many waves at this thing, if they are not completely in phase or close to one another, they just cancel each other out. Okay, so, and we're going to add this other qualifier. We only care about maximum intensity. Then the path difference. For them to be in phase with one another must equal n lambda. Okay. Why n lambda? You can use something called the Laue equations, which I really didn't want to spend the time to do. And you can show if you're bouncing radiation, you'll only get intensities where it's completely constructive. So this is completely due to complete constructive interference.
Oh, isn't there? What is
Yes. Yes, it is a laser. Actually, it's complete optics. Yeah. Okay. Well, sort of optics, material science, chemistry, physics. All right. Can we relate this to D? Yeah, because why else would we be wasting our time? Okay.
I use that.
Can I erase this junk here? Because I don't want to mess with my picture. Okay. Am I good? Okay. So first question, why only Completely constructive. Completely twice. In experiments, are we only going to use two waves? No. In experiments, we use way more than two. We're just using our two-wave example as an easy way to explain Bragg's law. Outside of complete constructive interference, you will not see anything. Because there's destructive interference that interferes. So, outside complete sorry, not here. Okay. As an example for this, we are each going to whisper a phrase. What phrase do you want to whisper? Not that one. How about crystallography? Let's do that. Okay, so about at this level, crystallography. I'm going to point at you, and you're going to say crystallography. Okay? Go, 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 go. Okay, now, it's kind of hard to hear that. We're all going to say it at the same time. Ready? Crystallography. You can hear it way louder. When they were doing this, they had film. They had to go with the brightest spots. If you have 1,000 people in a room doing that at different times, it's just going to sound like static. But if they all do it at the same time, you will hear the word crystallography together. So same sort of thing happens. So we only care about constructive. All right. Now, the other thing we said, what type of experiments are these? They're diffraction experiments, but specifically, what about the energy or the radiation? It's X-ray diffraction, yes. What type of collision do we have? Yes, elastic. Okay. Since interaction is elastic, what does that mean about the angle in and the angle out? We're not going to worry about, what was that? Yes, it's the same. Angle in is equal to angle out. Okay. How do we want to define our angle? I want a symbol. Theta. Okay. Where else do I need to draw theta? On the other side. Should be out. Okay. Now, what was it? Was it the Greeks or Romans that did a million things? Both of them? I don't know.
When you say a million things,
Trigonometry. So my family are all carpenters. They all know trig very, very well. If you ask them angles, like sine of 30 degrees, they all know it off the top of their heads. They also get incredibly frustrated with you when you try to read some measuring tape and you have to sit there like, okay, if I had 28 and 5/16, if I can't look at the tape immediately and spout that back to them, they get insanely mad. So working with carpenters is rough. let's put on our Greek or Roman hats and try and figure out how can we draw some triangles in this thing to relate these angles to what's happening to beta. What do you always look for in trigonometry? Triangles. Specifically, what type of triangle?
Right triangle.
You want to find a right triangle. Let's find some right triangles. If we go like this,
Hey, look.
and we draw a line directly down, what do we got here? A right triangle, yeah. On this side, what do we got? Yeah, a right triangle. Okay. Now, this angle in here, what's it equal to? It's equal to theta. Okay. If you ask me to demonstrate that, I have no idea. I don't remember how to demonstrate that. I just know this is true. It's like when a Gen Chem student asks me, like, x minus 6 is equal to 3. I can do the manipulation to both sides and get to that point, but they ask me, like, inherently why, and I go, I don't know. Like, I don't remember. It's just, like, part of me now. Same thing with trig. The abuse happens until you don't know why. Yeah.
You guys are the geometry let's say.
Nope. None of that. I'm sure there's somebody out there who does down the hall. Okay. So we have two right triangles here. Let's just consider one of the right triangles. We look at one triangles. Okay, so we got our triangle. Boop, boop, boop. Apparently you have to make those noises too. Theta is along here. What is our hypotenuse? Yes, it's the spacing between the lattice planes, D. Just because I want to kind of go with the Pythagorean theorem, I'm not really utilizing lattice vectors A, B, and C. Call that guy A, that guy B. Okay, then sine of theta. SOHCAHTOA, what do we got?
Opposite of the right.
So what would it be? B over D. Okay. Let's manipulate this around. Let's solve. We're going to get to D in a minute. But what is B equal to? Yep, sine of theta times D. No, my chalk. Okay. How many triangles do we got here? Yes. We have two. Well, okay, yes, excuse me. How many right triangles did we draw? That is a completely loaded question. You're right. How many triangles? An infinite amount. Yeah, well, I'm saying you could just keep bisecting this thing a gajillion times and end up with an obscene amount of triangles. How many triangles did we draw? Two. Yeah. So we have two drawn. Then the path length difference for these two guys. So how much further did B or beta travel in comparison to alpha? So here's D, right? It went an extra bit of spacing along here and an extra bit here to B. So it's that wave has traveled an extra 2B. The path length difference. And do you get what I mean when I say path length difference? Okay, just basically the difference that the radiation has traveled is 2b. Okay. What else is this also equal to? Yep. Hey, we have half of the Bragg law right now. Great. I'm okay to erase this bit, right? Okay. Now, we have two parts. Given that 2d sine of theta is equal to the path length, what else do we know is equal to the path length difference? Because we're kind of bound by maximum intensities. What does it have to be? Yeah, n lambda. So we can set these two equations equal to one another. 2d sine theta. And then originally we had this defined with sine on one side. Manipulate this. What's it going to be? Mm-hmm. Yep. You could have won a Nobel Prize. You're just kind of late. Yeah, I know. All the easy stuff is done. Now we're to the hard stuff. And then you know what they're going to say in 50 years from now? Same thing.